Okay, yeah, so good afternoon, everyone. Hey, yeah, sorry. Okay, welcome back to the PBA class, Physically Based Animation, for the 6th week. Yeah, today we will learn a new topic in the physics area. That is the laws governing motion, or as you can see here, yeah, in the image, we will learn about Newton's law. Yes, so that means we are going to introduce force to our moving objects. Yeah, a little bit of introduction about the discovery of these laws. Yeah, so as you may have known, the Sir Isaac Newton, which lived around 1643 to 1727. Yeah, he was an English scientist and mathematician. Yeah, he is more famous about the law of gravity actually. Yeah, when you take a look at this chief, yeah, when he sat behind, not behind, yeah, not, below an apple tree and was reading something. Then suddenly an apple dropped above him, and he wondered, yeah, how could the apple drop to the ground? Yeah, and he discovered the gravity. Okay, and he also discovered the three laws of motion, which we will learn today. Yeah, we know it as Newton's law of motion, or we can simply just call it Newton's laws. Yeah, it actually describes the motion of all objects on the scale we experience in our daily lives. Yeah, by introducing force. Yeah, so today we will learn about Newton's law of motion, which is a study on how the forces will affect movement of any object. Yeah, we have three laws to discuss today. Yeah, so now for short, the cause, this is the cause of movement. Yeah, force causes movement, which results in acceleration. Okay, then we will learn, yeah, tightly into the first law, which is the first law. Yeah, the first law states that when the force resultant on any object is zero, we can imply that F also zero. Therefore, A or acceleration is zero. Yeah, when the sum of all objects um, applied on in any object, then we can say that the acceleration is zero. The object either still or moves in a constant velocity. Yeah, so it receives or moves in a Kelvin fashion with a uniform velocity. Yeah, so the first law is very simple. Yeah, it is sometimes called the law of inertia, which states like this: yeah, a body remains at rest or moves in a straight line at a constant speed unless acted upon by a force. So we have two keywords here. Yeah, the object will move in a straight line and at a constant speed. But we must assume that there is no other force acted upon the object. When there is at least one object, then this law does not apply. Yeah, a moving object will still move unless acted upon by a force. Here I have actually two similar chiefs. Yeah, so we have a driver of a car and or a motorcycle. Yeah, as you can see here, the car will still move until it hits a brick of wall over here. Yeah, and assume that this brick of wall does not crumble, then by the other law of force, yeah, other Newton's law, then we can see that now this car stops moving, yeah, or actually it moves backward bit by bit. But in the second image or second GIF, you can see that the motorcycle stops moving. Yeah. And by the third law, later we will talk about the third law. Actually, there have some action and reaction forces acted upon this system. In this case, the driver and the car. Yeah, so that's why both on these two illustrations they uh, flung, flung out of their vehicle. Yeah, so that is actually the cause of the third law. Yeah, we will talk about it later. Yeah, that's all about the first law. Yeah, however, if the resultant of the force is not zero, yeah, if there is a force resultant F on any object, then Newton says that the momentum changes. The changes on a momentum equals to the given force. Yeah, momentum we will talk in more depth next week as the last subject. Yeah, but here I give you the rough formula. Momentum is denoted by P. Yeah, P equals to M multiplied by velocity. Yeah, and as we know from our kinematics, velocity is changes in displacement or distance over time. Thus, v equals to ds dt. And then acceleration is changes in velocity over time. Thus, a equals to dv dt. Yeah, then we can imply that any changes in the momentum equals to the given force. So F equals to dp dt. Yeah, the changes of momentum over time, and we can expand this to m times the changes in the velocity over time, which equals to m times a. Yeah, that's why we get the familiar formula F equals to m times a. But this highly assumes that the m, the mass of the object, does not change. Yeah, as you can see here, m is a constant, but the changes is in the velocity. Yeah, that's why we can derive m times dv dt is m times a. Yeah, or the sigma of F, the sum of all forces within an object, equals to its mass times its acceleration. Yeah, there are some cases when the m does change. Yeah, this is an example when the m changes and the v is actually constant in a spaceship launch. Yeah, because it burns the fuel, then actually the spaceship will lose its mass over time. So that's why in this case, F equals to V times the MDT. Yeah, the changes is now in the mass. The changes in mass over time, then multiplied by constant velocity. Yeah, anyway, we won't observe this type of momentum. Yeah, we will only observe when the m is actually constant. Yeah, so only the velocity changes. So we can derive this formula. Yeah, the sum of all forces within an object equals to the mass times acceleration. Yeah, the driving force causes the movement of any object. Yeah, and remember, you must sum all the forces that is applied in the particular object. Yeah, so we usually call it a resultant, or some people just simply says a sum of all forces. Yeah, in bahasa we also call it a resultant. Yeah. So in this illustration, we have a box, yeah, which is completely still. Then it is pushed or pulled by a force of F. So it will move with a constant acceleration A. So simply F equals to m times A. Now the third law, which is I think is more popular, yeah. When the object A applies some force F to an object B, then the object B will apply a similar force, but the direction is reversed. Yeah, so here the object B will apply force negative F to the object A. Yeah, so in this example, I think we can label this box as, let's see, this one is A, then this one is B. Yeah, if the object A applies a force F to the object B, and we can assume that the positive axis points to the right there, then the object B will apply a force a negative F to the object A. This is known as the action and reaction law. In this case, both forces happen simultaneously, happens on the same time, but take note that these two forces, they are applied to a different objects. So here I can denote this F in actually two ways. I can denote it by who applies the force and to whom. So I can denote this F as FAB, force given by A to a B. Then this one is force given by B to A. Or you can also use this notation. Where is my cursor here? You can also use this notation. So who is given the force first? In this case, this force will be FBA. So who gets the force and from whom? This means that this force F is actually a force on B by A. Force on B applied by A. In this notation is this is the F applied by A on B. There are actually two notations, and I think we will use let's see the second one. So we will write like this. If we have two objects, then we can denote this force is FBA, F on B by A. And since okay, so that means this one is no longer FBA, this one is FAB. We won't use this notation then. We will use the notation on what object by whom. Now, as you can see here, FAB is not does not necessarily means the same as FBA. So you cannot take the resultant of them, because they apply on the different object. In this case, in FBA, it applies on object B. In this case, FAB, it applies on object A. So you cannot really add them together. Remember this one. Remember this point. Forces are applied to different objects. So this is the definition for the third law. Whenever one body exerts a force on the second body exerts an equal and opposite. You must remember the keyword here is opposite. So we have some characteristic we can conclude here. It is equal in amount of force, but in the opposite direction, and it works on two different subject or object. Not subject. Just remember the keywords. It's equal but opposite and works on different objects. I think this law is easier to understand. If you have some trouble to remember it, then you can remember in daily life. Maybe if we punch or pull someone, then they will react. They will punch or pull we back. Most of the time. You can remember this to remember the third law. By the implication of the third law, now we are introduced to a friction F. A friction happens when two objects actually not really collide with each other. So for example, we have a person. This person is pushing a box on a floor. I think it's a wooden floor. We can actually draw the the forces in this system. Yeah. For now, just ignore the formulas. Yeah. What is Fs and what is Fk, mu s, mu k, and as well as n. Yeah. Just ignore this for now. Yeah. We will take a look at the system first. Yeah. So the person is pushing this box. Then we have a force on box by the person. Yeah. And as stated by the third law, then the box will exert equal but opposite force. Yeah. So this is a force on person by box. And if you take a look at the surface of this wooden floor, yeah, wooden floor, then because the box moves to the left, yeah, by the force, then actually the box will have some force on the floor caused by the box. Yeah, it's also to the left. Again, by the third law, then the floor actually will give some force in the opposite way, yeah, in the opposite direction. Yeah, this is the force on box by floor. Yeah, and this is what we call a friction. Yeah, we must have two surface here. Yeah, the surface of the floor itself and the surface of the box. Yeah, the reaction force is called the friction. And actually, we have a third system here. Yeah, with regard to the person itself, himself. Yeah, sorry, not not itself. Okay, so here, if we take a look at the blue arrows at the bottom side, yeah, we actually have this one is the force on the floor by person. Yeah, so maybe after this, when you observe yourself working, yeah, try to work more slowly in steps. Yeah, when we work, the first step we do is to push ourselves, yeah, against the floor. Yeah, and we push it to backwards. If we want to move forward, then the first thing we do is to push our feet backwards. Yeah, and then the floor will give a reaction in this blue. Where can I write it so you can see it? Yeah. This one is force given that by on the person by the floor, and this is the same. This is also a friction. Yeah. So as you can see here, by when we want to work, actually we have two forces applies on us. Actually, there is a third, but it is not drawn here. Yeah. The third one is force going upwards and downwards. Yeah, we will take a look later after this. Yeah, but horizontally, we can observe that there are actually two forces applies on ourselves when we want to work. Yeah, and actually, how we are able to work is caused by this action and reaction forces. Yeah, you can take a look later. You may want to search for the connection between working and forces. Yeah, and they will tell you that we can work actually because of this action and reaction law. Yeah, so everyday, even everyday tasks as such as working is actually influenced by physics. Okay, now let's observe in more depth what is friction, and actually we have two type of frictions here. Yeah, they are denoted by Fs and Fk. Yeah, what are these? So we have two type of frictions. Yeah, static friction and kinetic friction, and there are some text already here. When the object is still, yeah, is still, yeah, it's about to move. We can observe the system something like this. Okay, where's my cursor? Oh, here it is. Yeah, we have push force. Yeah, push or pull. It doesn't really matter. Yeah, we have some of force F to the right, and then uh, the floor will give the reaction as Fs. Yeah, this is a static friction when the object is still or does not move. Yeah, and we have two more forces here in a vertical axis, W, which is weight, and N, which is a normal force. Yeah, weight, as you may have known, weight is just mass times gravity. Where is the equation? Yeah, later. Yeah, weight is mass times gravity, and because this box lies in surface, yeah, the surface will give reaction force, which is what we call a normal force. Yeah, remember that normal force is always perpendicular to the surface. Yeah, here we only observe a flat surface. Yeah, if you remember from your high school, yeah, I will temporarily draw over here. Yeah, if you remember on your high school, maybe you have um, surface that is not flat. Yeah, but uh, using an angle, then you will have your box over here. Oops, sorry. You just now pretend this is a box. Yeah, and you will get the force downwards. Oops, it's still W over here, but for the normal force, yeah, you must draw it perpendicular to the surface. So if your surface is here, then your normal actually points over there. Yeah, but don't worry, we don't observe the angled surface like this. We only observe for the flat surface. Okay, so yeah, let me erase this one first, as not to confuse you. Oops, wrong pen then. Yeah, so we have n is negative w if you observe here. Only applies to a flat surface, yeah. The n and w is the same in the value, but differs in the direction. Yeah, so n is, let me write it here. N equals to negative w. Now, when the amount of force is still less than the amount of the static friction, then the object will not move. Yeah, only when the force is greater than the static friction, then the object will move with an acceleration of a. Yeah, so this only happens when F is greater than Fs. Yeah, if the force is equal or less than the static friction, then the object will not move. Yeah, if the object is moving, then we will observe Fk. Yeah, it's no longer Fs, but we observe Fk, which is a kinetic friction. Yeah, the object will move with a constant acceleration of a. Yeah, so first we must check if our F or our force is greater than Fs or not. Yeah, Fs, I must go back to the previous slide then. Yeah, Fs equals to the mu s times n. N is a normal force, yeah, in this case. N is a normal force, which is equals to negative W or negative M times G. Yeah, in the meantime, for mu s and mu k, we call it a coefficient. Coefficient of either static or kinetic friction. Yeah, mu s stands for coefficient of static friction and mu k stands for the kinetic one. Yeah. Mu s and mu k, we will always know it. At least in some exercises, yeah, in problems, in exams, you will always know the mu s and mu k. Yeah, but in real life, mu s and mu k is actually determined by two surfaces. Yeah, so you will always know the mu s and mu k at least in, yeah, later exercises. Yeah, when the object moves, then the second law applies. Yeah, the sum of F equals to MA. Thus, we have this resultant. Yeah, by using the second law in the x direction. Yeah, the sum of the force in the x direction equals to the mass times acceleration. We get F subtracted by Fk. Yeah, remember, because they are in the opposite direction, and we assume that the positive direction is pointing right, yeah, in the same direction as F. So that's why here you get F minus Fk equals to m times a. Then you can calculate the acceleration, yeah, by solving this equation. Yeah, F minus Fk equals to ma. Usually you will need to find the acceleration. Yeah, and at the right side, we observe the normal. Yeah, just remember that normal is perpendicular to the surface. Yeah, it always perpendicular to the surface with respect to the surface. So for flat area, this is simple. Yeah, the sum of the forces in the y direction equals to 0. Yeah, because in the y direction, our object does not move. Yeah, then we can simply say that n plus w equals to 0, thus n is negative w, negative weight, yeah, or negative m times c. Yeah, and if we assume that the positive axis points upward, then our uh, normal force will always be positive. Yeah, and for the w, it will always be negative. Okay, so there is the implication of having a friction in our object. Yeah, we have derived some new formulas. Yeah, let's take a look at how to apply them in some exercises. So I have the first exercise here. Yeah, a box with a mass of 5 kilogram is pulled with a force 25 Newton force to the right, and let G equals to 10, negative 10, yeah, negative 10 meter per second squared. We know that the mu s, the coefficient of static friction is 0.4, and the coefficient of kinetic friction is 0.2. Now we are asked A, check whether the box moves or not. Yeah, and B, calculate its, it is not velocity. Yeah, let me, yeah, I guess I will, if I remember, hopefully I remember to change the slide later. It's not velocity, it's actually acceleration. Yeah, or A in this case. Now, to solve this problem, we must do A first. Yeah, we must check whether the box moves or not. So if I have F here, F is 25 Newton, and the mass is 5 kilogram. Yeah, and we know mu s and mu k. Actually, before doing A, we can calculate W first. Oops. So let me correct my W. Yeah, the weight is, oh well, yeah, this one is W. I have M times G, and you can do M is 5, G is negative 10, so the weight is actually negative 50 Newton. Yeah, so you have the normal force. Assume that it is a straight line, yeah. N is minus W is 50 Newton. Yeah, now we have more information from the known values. Then we can calculate the static friction Fs, which is over here. We have Fs. Just calculate the static friction. Fs equals to the mu s times n. Mu s we know it's 0.4. Yeah, it's 0.4. And we know the normal is 20. Yeah, sorry, the normal is 50. Yeah, then we get the static friction is 20 Newton. Now check what is the relation of force and Fs. What is the correct relation between F and Fs over here?
F is bigger than Fs, sir.
Yeah, F is actually bigger than Fs. Yeah, our push force actually is bigger or greater than Fs. So the conclusion, the box moves. Yeah, so remember this, if F is greater than Fs, the conclusion is this one. Yeah, however, if the conclusion or the relationship is F less or at least the same as, yeah, as Fs, then this implies that the box does not move. Now we have answered A. Now we can calculate B. Yeah, what is its acceleration? Yeah, because we know that the box moves, then we must calculate Fk. Yeah, Fk equals to mu k times normal. Then we have mu k is 0.2 times 50. We have 10 Newton. And by the second law, yeah, the resultant of the sum of force, yeah, F negative Fk is equals to ma. 25 minus 10 is 5 times a. Then we have the acceleration of 3 meter per second square. Yeah, so this is a typical problem regarding to friction and Newton's law. Yeah, especially for the second law. Any questions maybe about this exercise, this problem? Yeah, not yet. Yeah, maybe because this is actually straightforward. Yeah, if you follow the steps, then you will get the same result. Yeah, just remember you must do A first before doing B. Yeah, so for example, maybe later in some more exercises, yeah, I will give more problems, more exercises for you to do. Yeah, I think I will give it next week. It's from a collection of problems and as well as the previous mid exams. Yeah, you can do it on your own. It is actually optional. If you don't wish to do it, then it's fine. Yeah, but if you do, yep, you can just work on the exercises. Yeah, some problem may skip A entirely. Yeah, so you are only asked to calculate its acceleration. Yeah, without A. So sometimes you won't get to check whether the box moves or not. Yeah, you are only asked what is the value of its acceleration. Yeah, even if you are tasked to directly calculate the acceleration, you must still follow these same steps. Yeah, so you must do check this one first. Yeah, this is required. This is the first step. Yeah, when the f is greater than fs, then you do the second step by solving the fk and so on. Yeah, when the f is less or equals to fs, you can safely say, yeah, because the box does not move, then the acceleration is actually 0. Yeah, sometimes I won't really tell you to check whether the box or the object moves or not. Yeah, you must consciously check it on your own. Okay, yeah. If there is no question, then let's take a look at the second one. So I have a 50 Newton applied force directs an 8.16 kilogram. I think it's not, it is translated here because the mass of this log is not the whole number. Yeah, but nevertheless, let's continue. Yeah. The log is dragged to the right across a horizontal surface. So we are asked what is the acceleration of the log if the force of friction is 40 Newton. Yeah, here, however, we don't really need to do step one because um, it is stated that the log actually moves. Yeah, so this one is simpler. We immediately jump to the second step. Yeah, remember that the sum of the force equals to MA. We have the force is 50, then minus the friction, yeah, which is FF here. Yeah, if we use our notation, then this is actually FK. Then this is only F. This one is M. Yeah, so I can rewrite this FA as F and this FF as FK. Yeah, it's only a matter of notation here. We will just simply use F, yeah, F and Fk. And actually to differentiate between force and friction, because friction itself is also a force, yeah, remember to write friction with lowercase f, yeah. So for Fk, don't write it as Fk, yeah. Please don't do this. We use a small or lowercase f out here. Yeah, just remember to use the lowercase f. It also applies with static friction, yeah. So use a small f, yeah, Fk and Fs. Yeah, although in this case the Fs does not exist, yeah. So we can continue our calculation. 50 minus 40 is 8.16 A. We get A is 1.23 meter per second square. Yeah, this one is simpler than the exercise one. Yeah, the standard is actually exercise one. So you can expect you won't get exercise two in your midterm exam. Yeah. The third one, a car with a mass of 2 ton or 2000 kilogram, was broken down on the street. Then how much push force should be applied so the car will move with the acceleration of 0.05 meter per second square. Here in this case, although the assumption is not really realistic, yeah, we have some assumption that the car will counter the kinetic force. So actually, the Fk here is 0. Yeah, if we can assume that the Fk is 0, so we have the second law, F equals to sigma F equals to ma, F minus Fk equals to ma, F because Fk is 0, so F is directly m times a, you will get 100 Newton. Yeah, this is even more easier, more simpler than the second and the first exercise. Yeah, this one is the illustration of using F equals to ma. Yeah, simply F is m times a because of this assumption. Yeah. Okay, because this one is the simplest one, so let's skip it to the fourth one. Now we have 3 boxes, M1, which is 10 kilogram, M2, which is unknown, and M3, which is 15 kilogram. Yeah, all of them lie on a flat rough surface with a UK is 0.1. Then a horizontal force F equals to 90 Newton is applied to the box 1. So all boxes moves with the acceleration of 2 meter per second square. Yes, so over here, where is my cursor? Oh, okay. Okay, we have the acceleration is 2 meter per second square. And we have the mass 10 kilogram. M2 unknown, M3 is 15 kilogram. Now, the question is how much does the second box weigh? Yeah, to answer this question, we will try to actually draw all of the forces applied in this system. Yeah. So because I have the force here, the easiest forces to draw are actually the kinetic friction forces. Yeah, I have Fk1 here. Then logically I have Fk2 as well as Fk3 over here. I won't draw the vertical forces here because they cancel out eventually. Yeah, because this is a flat surface, then N equals to W. Yeah, so I won't draw them. Yeah, but actually we have 2 more forces over here. I have this force. Yeah, it is a force on 2 by 1. And this one is force on 3 by 2. This one I can name it as F, simply F1. Yeah. Force on box 1 from whoever push it. So I can just simply name it F1. Yeah. Now to actually calculate the second box weight, let's just calculate first for the kinetic frictions for all of these boxes. Yeah. We must calculate the normal forces first, and 1 equals to 10 times 10. Remember the G is 10, yeah? 10 times 10 is 100. N2 is 10 times M2. And the third normal, N3, is 15 times 10, which is 150 Newton. Now for the kinetic frictions, yeah, simply Fk1 is mu k times N1. the mu k is 0.1. 0.1 times 100 is 10. 0.1 times 10 m2 is m2. And 0.1 times 150 is 15 Newton. Yeah, now we must take a look at the sum of the forces in the whole system. Yeah, we will observe the whole system, and because it moves, then we can also observe the mass times acceleration. Yeah, but here in this case, because we have three boxes, we must calculate the sum of the masses as well. Yeah, that's why for the resultant of forces, we have F minus F1, Fk1 minus Fk2 minus Fk3 equals to the sum of the masses, yeah, m1 plus m2 plus m3 times acceleration. Yeah, we know the acceleration is 2. Then we know everything else. Yeah, the resultant F is 90. Then Fk1 is 10. Fk2 is m2. Fk3 15. And everything else, m1 is 10. M3 is 15. You solve this equation, then you will get the mass of the second box is actually 5 kilogram. Now, for the second question, calculate the push force given by box 2 to box 3. Yeah, so, oh, the notation is reverse. Yeah, I think. Push box on of box 2 on box 3. Here it is denoted by F23. Yeah, if I can separate the third box from the rest, yeah, I can draw it something like this. Yeah, this is the third box. Yeah, for the third box, I have F. The notation is reverse. So this is the force given by 2 on 3. Yeah, or using our notation is actually F32. Yeah, it's the same. And we also have the not static, the kinetic friction of box 3, Fk3. Yeah, in the third box, that's all the forces applied on the horizontal axis. Yeah, we don't need to include F21 because F21 is not for is not applied to box 3. Yeah, so the diagram for the forces in the horizontal direction for box 3 is only two forces, yeah, F23 or F32 in the right on not the right on the left diagram, yeah, and Fk3. So if we calculate the sum of F3, which is still equals to M3 times A, you will get this one, yeah. F23 minus Fk3 equals to M3 times A. We know everything except for F23. Yeah, Fk3 minus Fk3, I can move it to here. So F23 equals to M3 times A plus Fk3, which is when we solve this, we get 45 Newton. Yeah, that's how you solve the fourth exercise. Any questions? Maybe. I guess not yet, yeah. Should you have any questions later, just ask me in the group chat then. You can use Hangouts or the WhatsApp group, yeah. Okay, if you don't have any questions, then it's time for Unity. Yeah, so that's all about the Newton's law. For the Unity part, yeah, I have already provided the video in Google Classroom, yeah, as usual. It's about force and friction. And remember, starting from this week, we will use rigid body. Yeah, so you don't really need to simulate everything from scratch. Yeah, if you want to do this from scratch, then you must carry over the KLBB part. Yeah, just use rigid body. So you must continue from the last week's project. Yeah, you must use your week 5 Unity project, then do everything as instructed here. Yeah, you will simulate for force first, yeah, with no friction, and later uh, you will simulate friction as well using our beloved car over here. Yeah, just assume that your car moves in on a surface, yeah, on the road, and you can assume the blue, yeah, the blue rectangle in the screenshot is actually the road. Yeah, if you want, you can also search for the road sprite and add it to your simulation then. Yeah, but it does not really matter. Yeah, the only one that matters is the correct simulation for friction and force beforehand. Yeah, yeah. Everything else is already described here, and I have already provided the video for you. So after this, you may leave the this meet, yeah, and continue to the lab session. Yeah, I will be still here as always until maybe 3 or 3:15. Yeah, you may continue to your lab session then.